Okay, let's start. So today we'll solve the assignment 5 for the course Linear Algebra, NOC 23, MA 23. So I have a tutorial. Okay, let's come to the first question. So what it is saying, consider the bases beta and gamma, two bases are given of R2, and a matrix, two matrices are given. So you have to find the change of basis matrix of the identity transformers with respect to both the bases beta gamma and gamma beta. And we have to find means what will be the change of basis matrix you have to find. Okay, so beta 1 2 and 2 1, this is one basis, and gamma 2 3 1 4, these are the two bases for R2. So identity transform, what does it do? So I will take the same vector 1 comma 2 to 1 comma 2, and now you have to write 1 comma 2 in terms of the basis gamma. So let's suppose we can write it a into 2 3 plus b into 1 4. Then we will get to system of equation. So what we will get, 2a plus b equals to 1 and 3a plus 4b equals to 2. So you have to solve these two equations. So let's solve. So multiply this first one by 4 and the second one by 1 into 4, and then subtract. So you will get 8a plus 4b equals to 4, 3a plus 4b equals to 2. So if you subtract, you will get 5a equals to 2, or a equals to 2 by 5. So what will be then b? So b will be 1 minus 2a, 2 into 2 by, sorry, this will be 5. 2 by 5 means 1 minus 4 by 5. So 1 by 5. So therefore we can write I of 1 comma 2 as 2 by 5 into 2 3 plus 1 by 5 into 1 comma 4. So this we have done for 1 comma 2. Similarly you have to do for 2 comma 1. So let's do it. I of 2 comma 1. So it will again identity map will send it to the same 2 comma 1. Again you have to write it in terms of the basis of gamma, a 2 3 plus a b 1 4 b into 1 comma 4. So what you will get from here, 2a plus b equals to 2 and 3a plus 4b equals to 1. Then now I can solve these two system of equations. So suppose if we name it 3 and 4, so multiply 3 by 4 and subtract from 4. So what you will get, 8a plus 4b equals to 8 and 3a plus 4b equals to 1. So here we will get 5a equals to 7, or a equals to 7 by 5. Then b will be 2 minus 2 into 7 by 5. So you will get minus 10 minus 14 by 5 minus 4 by 5. So I of 2 comma 1, this you can write as 2 comma 1 equals to, sorry, 7 by 5, 2 comma 3 minus 4 by 5, 1 comma 4. Then what will be the matrix corresponding to this transformation? So how to write? So means we have to write in terms of column wise. Okay, so let me write it again. What we have got, I of 1 comma 2, we have got 5 by 2, 2 comma 3 plus 1 by 5, 1 comma 4, and I of 2 comma 1 we have got 7 by 5, 2 comma 3 minus 4 by 5, 1 comma 4. So the change of basis matrix with respect to beta gamma will be, it will be 2 cross 2 matrix. So first you have to write down the coefficient column wise. 5 by 2, 1 by 5, and for the second one again you have to write it column wise. So it will be 7 by 5 minus 4 by 5. So we get the change of basis matrix. Now let's see what we have to find. So it's given that you have to find the value of 5a. So here a is the a11 element, here is the a that you have to find. So a is 5 by 2, sorry 5 by 2 or 2 by 5, it's 2 by 5, not 5 by 2, it's 2 by 5. So you have to find 5a. So 5a, so comparing with the matrix, this comparing with what, a 7 by 5, 1 by 5 d, we get a equals to 2 by 5. So 5a will be 5 into 2 by 5 means 2. So the answer is 2. Okay, so the first question is done. Let's move to the question number 2. Here you have to find the value of 3b. So again comparing with the matrix, what is the b? Oh, for that we have to find the second matrix, b, identity matrix with respect to, this is gamma beta. Okay, let's find it. So for that you have to, so here we have to find, because b is in the second matrix, let's see, here b is in the this part, identity beta gamma. Here we have to find identity with respect to gamma beta. So I of, you have to find 2 comma 3. It will send 2 comma 3 to 2 comma 3, and then you have to write 2 comma 3 in terms of 1 comma 2 and 2 comma 1. So you have to find the coefficients. So you will get two system of equations, a plus 2b equals to 2 and 2a plus b equals to 3. Okay, then let's solve these two equations. So multiply the second one by 2, you get a plus 2b equals to 2 and 4a plus 2b equals to 6. Then subtract both these two equations, we'll get minus 3a equals to minus 4, or a equals to 4 by 3. Then what will be? B will be 3 minus 2a, a is 4 by 3. 9 minus 8 by 3 means 1 by 3. So I of 2 comma 3 is what you have got, 4 by 3 1 comma 2 plus 1 by 3 into 2 comma 1. Let's find the other one, identity of what it is, the second 1 comma 4. So 1 comma 4 now you have to write in terms of a 1 comma 2 plus b 2 comma 1. Okay, so this time we have a plus 2b equals to 1 and 2a plus b equals to 4. So if we solve these two equations, then what we will get? So let's eliminate b again. So a plus 2b equals to 1, 4a plus 2b equals to 8. Minus 3a will be minus 7, or a will be 7 by 3. And then what will be b? B will be 4 minus 2 into 7 by 3 means minus 2 by 3. Right? Yes. So identity of 1 comma 4 equals to 1 comma 4, which will write 7 3 1 2 minus 2 by 3 2 comma 1. So what will be the corresponding change of basis matrix? So let's write it. I with respect to gamma beta, right? So gamma beta, it will be, what will be the what are the coefficients? Here it is 4 by 3 1 by 3. So you have to write it in the column. So 4 by 3 1 by 3. Not in the next coefficient, 7 by 3 minus 2 by 3. 7 by 3 minus 2 by 3. Now I can compare with the second matrix. What is the second matrix? 4 by 3 b c minus 2 by 3. So comparing with 4 by 3 b c minus 2 by 3, we get b equals to 7 by 3. Right, then let's see what we have to find. We have to find 3b. So just multiply with 3. Therefore 3b will be 3 into 7 by 3 means 7. So the answer is 7. Right. So 2 is also done. So let's move to 3. Here we have to find the value of 6c. C is in the second matrix. So comparing with this, what will be the value of C from the above equation, from the above question? We can see that what will be the value of C? C equals to 1 by 3. Right, and then what will be 6c? 6 times c, it will be 6 into 1 by 3 means 2. So the value of 6c is 2. Okay, so this is done. And the next one, you have to find the value of 10d. So this you will find from the first equation, 10d, because d is in the first matrix. So from the first question, what you will get, d will be, so d will be minus 2 by 3 from the first question. We get d equals to minus, what will we get, d equals to minus 4 by 5. We get d equals to minus 4 by 5, then 10d will be, then 10d will be 10 into minus 4 by 5, means it will be minus 8. So the answer will be minus 8. Okay, so question number 4 is also done. Okay, let's move to question number 5. Okay, so here what you have to do, a vector space V is given and V star be the dual of V. Then you have to find which of the following statements are true. What is the first option? Say there is a finite dimensional vector space V such that dimension V is greater than dimension of V star. Okay, so you have to say that this is true or false. So for finite dimensional vector space, you know that dimension V and dimension V star are always same. This was done in the class. Or simply you can give the, so assuming the basis of V, you can define, means you can give the basis of V star. So how to do that? So let's say for finite dimensional given, so let's say dimension of V is n. So and the corresponding basis, let u1 dot 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 en be a basis of V. So we will now define the basis of V star. How you will define this? So V star are the set of linear functionals, right? So they are linear map from V to R. So V star, they are all like functions. So we define fj from V to R by fj of ei by Kronecker delta ij. Right, so this is what is Kronecker delta ij. This is 1 if I equals to j, and otherwise it will be 0 when I not equals to j. So you can show that this forms a basis for V star. So one can check easily. That this f1 f2 dot 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 fn, so for j equals to 1 less than j less than n, you can define, right? So f1 f2 fn, this will be basis of V star, set of linear functions on V. So corresponding to u1 to n, we get a number of functions f1 f2 fn which forms the basis of V star. So means dimension of V star is, which implies dimension of V star is also n. Therefore, so for finite dimensional vector space, dimension of V is equals to dimension of V star. Dimension V equals to dimension of V star. So the first option is false. It's saying that there is a finite dimensional vector space for which dimension of V is strictly greater than V star, which is not true. The first option is false. Okay, let's move to the option number 2. What it is saying, for x belongs to V, if fx equals to 0 for all linear functionals, then you have to say that x equals to 0 or not. So let's check this. What it is saying, for x belongs to V, given that fx equals to 0 for all f in V star, means for all the linear functional in all the linear functionals in V, right? So then we will show that x will be 0. So we will show x equals to 0. Okay, how to do that? So you have said that what will be the basis for V star for dual basis, fj, right? So because x belongs to V and suppose if V is a dimension n, so then let dimension of V is n and ei dot en be a basis of V. Then you can write x equals x in terms of u1 e2 n, right, which imply you can write x equals to a1 u1 plus a2 e2 plus dot en, where a1 up to n these are scalars. Right, so now let's apply the basis vectors, means fi over x. So let's suppose apply for fk. I am for fixed k, I am applying. Let's apply fk on x. Then what will happen? So fk of x will be fk of a1 e1 plus dot a n en, right? And because fk, these are linear functional, means these are linear, so a1 e2 n will be came up from the function a1 f of fk of e1 plus dot ak fk ek plus dot an fk en. And what it is given that fx is 0 for all linear functionals. So fk is in particular linear functional. So for this it will also hold. So which implies, so therefore, first note that what will happen if we apply fk over this. So because fk of ej, we know these are Kronecker delta ij, right? fj of ei are the Kronecker delta ij, means only when I equals to j this will be 1, otherwise it will be 0, right? So only the kth term will be non-zero, otherwise everything will be 0. So this will be 0 plus dot 0 plus this will be only 1, fk ek will be 1, so ak will be only non-zero, plus 0 plus dot 0. So what you get? ak you will get. If we apply fk over x, you will get the ak, means the coefficient corresponding to the basis ek, right, only will be non-zero. And now, so as fx equals to 0 for all f in V star, so therefore applying f1 f2 fn, f1 f2 fn, we get, what we will get, f1 of x 0 imply a1 will be 0, right? And like similarly f2 of x, if you apply of 0, you will get a2 will be 0, right? And if you apply fn of x to 0, you will get an equals to 0. So you get all the coefficients are 0, means therefore x equals to, as we have x equals to a1 e1 plus dot an en and all the coefficients are 0 means x is itself 0. So we have proved that if fx equals to 0 for all f in B star, then x should be 0. So that second option is correct, right? Okay, let's come to the third option. What it is saying, there exists a linear functional on R3 such that f of 0, 0, 1 will be 2. So this is option number 3. It is saying that there exists f in R3 star is the dual linear functional on R3 such that f of 0, 0, 1 equals to 2. So this is a non-zero vector, right? 0, 0, 1 in R3. So you have to find a linear functional so that it will take the values on 0, 0, 1 equals on it will be 2. So let's define. So we have to show this, right? Because we want a linear functional, so it's enough to define on the basis, and from there we can extend it linearly, right? And so what are the bases for R3? Let's take the standard basis. So let's take E1, E2, E3, the standard basis of R3. Basis of R3. What are the E1? What is E1? E1 is 1, 0, 0, right? E2 is 0, 1, 1. 0, 1, 0, and A3 is 0, 0, 1. So these are the basis for R3. So it's enough to define on the basis vectors, means on E1, E2, A3. So let's define f from R3 to R. First we want at 0, 0, 1 it should be 2, and so we can define 2 to be all the other basis vectors. So let's define f of 1, 0, 0, 1, 0, 0 itself to be 2, and f of 0, 1, 0 also 2, f of 0, 0, 1 to be 2. So we have defined it on the basis. Now how we will extend it to the whole R3? Just by linearly. Sorry. Okay, now extend it f linearly to R3. So what is the meaning of this? How to extend this linearly for R3? Because so it means you have to define in arbitrary vectors, right? So let's say x, that x is in R3, means x will be A1, A2, A3. So this you can write in terms of basis vector as A1, E1 plus A2, E2 plus A3, E3, right? And now you know the action of f on the basis vector. So what will be f of x? F of x will be A1, f of E1 plus A2, f of E2 plus A3, f of E3. And you know all the three, so you completely know what will be the value of fx, right? So this is the meaning you extend the f to linearly on R3, whole R3. So the function is now well defined. So now you can also see that f also take the value 2 on the 0, 1, 0, right? Or 0, 0, 1. What it is? 0, 0, 1, right? And this is linear, right? Because this is by the means how we define the function. So we get a linear function on R3 which satisfies the condition f of 0, 0, 1 equals to 2. So the option number 3 is also correct, right? And now what is the next option? You have to say there exists a linear function on an R2 such that f of 0 0 is 1. Does there exist a linear function which satisfies f of 0 0 equals to 1? You know that f are linear functional, right? So linear map. So it should send 0 vector to the 0 vector, because 0 0 is a 0 vector of R2, but 1 is not the 0 vector of R. So there should not exist any such linear functional, right? So let's see what option number 4, what it is saying, that there exists. So we'll show that there saying that there exists a f in R2 star such that f of 0 0 equals to 1, right? So suppose if such f exists, then what will happen? So let's see. So if such f exists, then where the 0 vector will go? F of 0 0. So this 0 0 you can write by x comma x or x comma y, any vector, minus x comma y, right? This is again 0. And now because f is linear, so what will happen? F of x comma y minus f of x y, right? As f is linear. So then you will get, suppose f of x y is, take the value, some say, let's say k, so it will be k minus k. Let f of x y is k, right? So you will get 0. So f of 0 0 should be 0, means there does not exist any linear functional which will take f of 0 0 to 1, which implies there does not exist any f in dual of R2 such that f of 0 0 is 1, right? So the option number 4 is again false. Okay, so let now move to the option number 5. It's saying that if B is a finite dimensional vector space, then dimension of B is dimension of B double star, means double dual. So what is the double dual? It's the dual of the dual, right? So option number 5, what it is saying, if B is a finite dimensional vector space, then dimension of B equals to dimension of B double star. So we know, we have done that dimension of B equals to dimension of B star, right? And what is B double star? As B double star is basically B star whole star, right? Dual of B star. So as we know, and we also know that, we know dimension of B equals to dimension of B star, right? And B star is again a vector space. So now replace B by B star, then what you will get? So this is, let's say 1, replace B by B star in 1, then you will get dimension of B star will be dimension of B double star, right? So from 1 and 2 you can clearly see that dimension of B is equals to dimension of B star. Therefore from 1 and 2 we get dimension of B equals to dimension of B double star. So option number 5 is also true. Okay, now came to the question number 6. What it is saying, if B is isomorphic to W, then B star is isomorphic to W star, right? So what is the meaning of B is isomorphic to W? Means there is a invertible linear map which takes B to W, right? Means invertible linear map from B to W. Then you have to prove that there will be a invertible linear map which will take B star to W star. So what is the option number 6? If B is isomorphic to W, B is isomorphic to W, then B star is isomorphic to W star. So, and you know, for finite dimensional vector space, dimension, if dimension of two vector space are equal, then they will be isomorphic, right? So dimension of B is isomorphic to W, it's given. So their dimension will be equal, right? So given dimension of so let's write it properly. As B is isomorphic to W, which implies dimension will be same, right? Dimension of B equals to dimension of W, and we already know the dimension of B and dimension of B star are same. We already know dimension of B equals to dimension of B star, and the same will also hold for W, and dimension of W equals to dimension of W star, right? So from there we can see that therefore dimension of B star will be dimension of W star, right? Therefore dimension of B star will be equal to dimension of W star, and B or W both are finite dimensional, so if dimension are equal imply B star and W star are isomorphic, which imply B star is isomorphic to W star, right? So option number 6 is also correct. So option number 6 is also correct. So question number 5 is done. Let's move forward to the question number 6. Okay, what it is saying, let T be a linear map from MN to MN linear, it's not prior it's said. So what is it? T is a map is given, T of the whole matrix, it sends to the sum of the all the entries. And you have to check that T is linear or not, linear functional or not, right? So what it is, T is MNR to R. So MNR is a set of n cross n matrices. So means let's say A11 dot 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 A1n dot dot AN1 dot 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 ANN. How it is defined? It sum the all the entries. Summation ij equals to 1 to n aij, right? So for 2 cross 2, let me explain what is how the map is defined. So let's say n equals to 2. Suppose this is the matrix T, suppose 1 2 3 4. So how it will map? So T is from M to R to R. So it will simply add all the elements 1 plus 2 plus 3 plus 4 8 9 10, right? So this is the map. This is how the map is defined. So you have to check this is linear or not, right? So you have to take two matrices, add, and you have to see that this satisfy or not. So let's take two matrices. So this is just for remark. Let A equals to Aij, Ij, I comma j, and Bij, I comma j. They belongs to M and R. Then add these two, T of A plus B. What it will be summation. So this will be basically look like this, T of Aij plus Bij of Ij. So it will make a map summation Ij equals to 1 to n Aij plus Bij. Now simply write it like this, I comma j equals to 1 to n Aij plus summation Ij equals to 1 to n Bij. So this is the T of A and T of B. So T of A plus T of B. Right, so we get T of A plus B is T of A plus T of B. Now let's that this is linear or not under this scalar multiplication. So take C any real number. Then what is the T of CA? So this is the matrix C Aij of Aij. So this will be Ij equals to 1 to n C Aij. Now take out the C from the sum because this is not dependent on Ij, and Ij equals to 1 to n Aij. So this will be basically C of TA. So this is again linear under the scalar multiplication. So therefore T is a linear, and as T map from M and R to R, so it is a functional. So this is a linear functional. And therefore T is a linear functional. So the option number 1 is correct. Okay, now what is the option number 2? T is 1 to 1 for all natural number n or not. So this map is 1 1 or injective or not. So let's check. Injective means it should be sent to different vector right? So we will show that this is not 1 1, right? So for all n you have to show. So it's enough to give counterexample for some particular n. So let's take n equals to 2. And what will be then map? So T is basically map from M to R to R. So let's take T of 1 0 0 minus 1. So what it will be 1 minus 1, it will be 0. And again, and what will be under T? Let's take minus 1 0 0 1. This will be again minus 1 plus 1, so the sum will be 0. So we see that these two are different matrices in M to R, but they will map to 0 both. So which implies T is not 1 1. T is not 1 1. Right. So the option number 2 is false. Because we showed for M to R, this is not true. So this will not for any natural, means not true for all natural number. Now we have to check the T is on 2 for all natural number or not. So option number 3, you have to check that T is onto or not. So what is the map? T from MN to R, right? T of Aij is I comma j is summation Aij. So to show onto means you have to take any number from R and you have to find a matrix which will map to that under T to that number, right? So let's say X in R or V, let's say V in R. So you have to find a matrix so that T will map that matrix to V. So because this, what does this linear transformation does? It will sum all the entries. So you can simply take this T, take this matrix V and all the other entries are 0, right? So this is a n cross n matrix where all the other entries are 0. So here it will map, it will be mapped to V plus 0 0 0 0 0, right? So it will be simply V. So for V in R we get a matrix and note as this matrix B 0 0 0 0. This belongs to Mn of R. You can always find such matrices. So therefore T will be onto. Therefore T is onto. Right. So this linear map is 1 1, not 1 1 but onto. Linear functional, right? So T is onto. Option number 3 is correct, and this you can do for all natural numbers for all n, right? So this is done. You have to find the nullity of T. So what will be the nullity of T? Nullity of this linear transformation. Option number 4. So T is a map from MN to R, right? So you can apply the rank nullity theorem. So for that, what you have to find? You have to find the dimension of MNR and R, right? So this is, so V is here MNR. So what is the, you know the dimension of MNR? As we know, dimension of MNR, this was done in the previous assignment. Dimension of MNR is n square, right? And dimension of R, what is the dimension of R? Is 1. And T is onto, right? Also T is onto by option 3. So this is the range, dimension of the range space is also 1, which implies dimension of the range space or rank, simply rank of T. Rank of T is also 1. So you get, so by rank nullity theorem, rank of T plus nullity of T equals to dimension of MNR, right? And you know the rank of T is 1, so you have to find the nullity of T, and dimension of Mn and R is n square. So from here we will get nullity of T is n square minus 1, right? So let's see what is the option. It's saying the dimension, the nullity of T is n square minus n. So this is false. So the option number 4 is not correct. And now it's saying that T is invertible for some natural number or not. So you can, so when T will be invertible, and we know that because T is onto, So let's move on. So it is option number 5, right? So you have to find that we have to check that T is invertible or not for some n. So for that we have to check that T is 1 1 or 1 2, right, bijective, because T is linear, we know. So it's I have to check T is 1 1 and 1 2. So and we know T is 1 2. So we have to check that T is 1 1 or not. So T is 1 1 if and only if nullity of T is 0, right? And T is 1 1 if and only if nullity of T is 0. And what we have got from question number 4, the nullity of T is n square minus 1. So this should be 0. So therefore n square minus 1 should be 0 from this 4, right? Which implies n square should be 1, and n is a positive natural number, so n should be 1 as a natural number, so n can't be minus 1. So for n equals to 1, T will be 1 1, right? So for n equals to 1, T will be 1 1. So for n equals to 1, T will be 1 1 and 1 2, means T is invertible, which implies T will be invertible. For other n, it will not be invertible, so T will be invertible for n equals to 1. So the option number 5 is true, because it's saying that T is invertible for some n. So we get for n equals to 1, T will be invertible, so option number 5 is correct. Okay, so question number 6 is also done. So now question number 7. What it is saying, V and W be finite dimensional vector spaces over R and U be a proper subspace of V. So each of the following statements are true. Okay, what is option number 1? Any affine subset U plus U in V contains 0 vector. Any affine subset, it's saying that. So this is not true, right? Or why this is not true? So V and W are finite dimensional vector space. Finite dimensional over R, and U is a proper subspace. So note then what is meant by proper means and U is proper subspace of B, means there is a element in B which does not belongs to in U, which implies there is some, let's say V naught in B minus U, right? So means this is not the entire subspace U. So there are element outside U which is not outside B, outside U which is in B, right? So take then this affine subspace U V naught plus U, then take the following affine subspace. following affine set. This is not a subspace set, these are affine. V naught plus u. Then does V naught contains the zero vector of V? Then we claim that V naught plus u, that this affine set will not contain the zero vector of V. Then V naught plus u claim, this is the claim, will not contain zero vector of V. Right? So U is a subspace. So suppose 0 is in there, so means, so if 0 should be there, so means if 0 belongs to V naught plus u, which will then imply 0 you can write as V naught plus some u, which imply V naught equals to minus u, and where u is in capital U. So which imply V naught belongs to u, but this is a contradiction because we have chosen V naught outside u, which imply V naught belongs to u. So this is a contradiction. Contradiction as V naught belongs to V minus u, right? So so V naught plus u will not contain any zero vector, right? So we are done. Therefore V naught plus u, so this is the proof. Will not contain zero vector of V. So first option is incorrect, false, right? Okay. Let's what is the second option? It's saying any two affine subsets of u1 plus capital U and u2 plus capital U in V are either disjoint or the same. So let's do it. So u1 plus u, this, and u2 plus u2 are two affine subsets. So you have to say that they are either disjoint or the same. So suppose, so if they are same, then we are done. So if u1 plus u equals to u2 plus u, then we are done. So if they are not same, and suppose so assume that there is a non-trivial intersection. So let's say some V belongs to their intersection u1 plus u intersection u2 plus capital U, right? Then you have to show that they will be same, right? Otherwise, yeah. So means there cannot be a non-trivial intersection. You have to show. If they are not disjoint, so if they are disjoint, then we are done. That will be better to say. So if are disjoint, then we are done. So suppose they are not disjoint, means there is some vector which is in the intersection. So then what will happen? Then you can write V equals to u1 plus some, suppose u prime. You can also write u equals to and. So how to say this? So which imply you can write b equals to u1 plus some u prime equals to again some u2 plus some u double prime, right? For some u prime and u double prime in u, right? So from there what will happen? Then you can say that u2 minus u1, then u2 minus u1 will be, so u2 minus u1 will be basically u1 will be b minus u1, b minus, oh sorry, let's write it here, then u2 minus u1 will be b minus u double dash minus b minus u dash, it will be plus, so it will be u dash minus u double dash which is in u, so u2 minus u1 lies in u, right? So therefore u2 plus u will be u1 plus u, so which implies they are same, right? So we have shown that if there is some element in the intersection, then they will be same. So either, so any two affine subset either will be disjoint or will be same. So option number 2 is also correct. Okay, now move to the option number 3. What it is saying, image of any u in u under the natural surjective map v goes to vu is 0. So option number 3, what it is saying, image of any u in u subset of v under the natural surjective map. This was done in the class, means what will be the natural surjective map for the cosine space. Surjective map v goes to v mod u is 0. So what is the natural surjective map from v to the cosine space? So v to, let's say this is by pi, denoted by pi from v to v by u. So pi of v, you have to just v plus u, just write, right? And you can so check that this is well defined map, right? So you basically send it to the coset of v. So this is the natural surjective map, and you can check also that this is surjective. Then what will be the image of u? Then image of u means what will be the, then for u in u, pi of u will be u plus u, so which is basically u. And what is the zero vector in cosine space v mod u, and u is the zero space, right? So which is the, as u is the zero element in v mod u, so pi of image of u, therefore image of u is the zero vector under pi, right? So option number 3 is also correct. Now let's move to option number 4. You have to find b cross w. This is the product of two Cartesian product of two vector spaces. You have to find the dimension of b cross w. So you have to, it will be dimension of b plus dimension of w. So this is the option number 4. So let's say dimension of V is n and dimension of W is m. Let's say V1 dot 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 Vn be a basis of V and W1 dot 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 Wm be a basis of W. So from there we have to find a basis of V cross W. So what is V cross W? So this is the ordered pair, right? V cross W. So this is contains all x y ordered tuples such that x is in V and y is in W, right? So let's claim what will be the basis for V cross W. So we'll claim that this set Vi, 0 union 0, Wi. Let's not write in this way. Claim Vi, 0 such that Vi belongs to, let's say this is beta, this basis, and this is gamma. Vi belongs to beta union 0, Wi such that Wi belongs to gamma will be basis of V cross W, right? Okay. So how many elements are there in this set? So let's take this set to beta. So you can check that here these are n number of elements and here m number of elements are there. So cardinality of eta is basically, therefore cardinality of eta is basically n plus m. Now if we show that this, so there are n plus m number of elements, if we show that they are linearly independent and they span the V cross W, so then they will be the basis of V cross W, right? So how to show they are linearly independent? So let's check. So suppose, so we'll first show this eta is linearly independent. So let's A1 V1, 0 plus dot 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 An Vn, 0 plus B1, 0, W1 plus dot 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 Bm, 0, Wm is 0. So then you have to show that A1 up to An, B1 up to Bm are 0. So then what will happen? It will be A1 V1 plus dot 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 An Vn, then other will be 0, comma, it will be B1 W1 plus dot 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 Bm Wm. This is 0. So this is 0, this is 0 vector in V cross W, right? So that they will be component wise, they will be 0. It will be A1 V1 plus dot 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 An Vn will be 0 and B1 W1 plus dot 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 Bm Wm will be 0. And now V1 up to Vn are the basis of V, and this is 0 vector in V. as v1 up to vn and w1 up to wn are basis of v and w respectively. So therefore, they are basis and linear combination of this sum equals to 0. So a1 up to, which imply a1 equals to a2 equals to dot 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 an equals to 0, and similarly for b1, right, b1 equals to b2 equals to dot 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 bm equals to 0. So we get all the coefficients are 0, which implies that this set eta is linearly independent. Right, so we have shown that eta is linearly independent. Now we have to show that eta will span v cross w. So let's check. Eta spans v cross w. So means, so you have to take an arbitrary element and you have to write down in terms of the basis, in terms of the element of eta, right? So let's take arbitrary elements x from v cross w. So how it will look like? It will look like x is, which imply x will be some, let's say pq, p comma q, where p is in v and q is in w. And so p is in v and v1, v2, vn is a basis. So which imply p you can write summation of a1 v1 plus dot 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 a and vn. Why you can write as v1 up to vn is basis of p v. Similarly, you can write q. Similarly, what will be q will be some for where a1 an will be some real number, b1 w1 plus dot 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 bm wm, and where again b1 up to bm will be in r. So you have written down pq in terms of the basis of v and w. Then what will be this? So if we write it down, so x is p comma q, and this we have written down a1 v1 plus dot 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 an vn comma b1 w1 plus dot 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 bm wm. So this will be m. So if you write, so note that this you can write a1 v1 comma 0 plus dot 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 an vn comma 0 plus b1 0 comma w1 plus dot 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 bm 0 comma wm, right? So you have seen that any x can be written down, and where these are all the elements of eta, where v1 comma 0 dot 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 vn comma 0 0 comma w1 dot dot 0 comma wn m belongs to eta, right? So which is the means that this set spans v cross w, which implies span of eta is v cross w. So this is indeed the basis of v cross w. So therefore dimension of v cross w is n plus m, which implies dimension of v cross w is n plus m, and n is the dimension of v which you have taken plus dimension of w. So you have shown that dimension of v cross w is dimension of v plus dimension of w. So option number 4, I think 4 is also correct. And now you have to find the dimension of the quotient space v mod w. So we have to find a basis for V mod W, the quotient space. So this is the option number 5. So we have to find find dimension of V mod W. V mod U. So let's say dimension of U is some M. Let dimension of U be M and take the basis some x1 up to xm be a basis of U, and U is a subspace of V, as U is a subspace of V. Subspace V. So you can always extend the basis of U to the whole of basis of V. So extend the basis of U to the whole of V. Extend the basis of U to the basis of V. So let's say x1 up to xm comma xm plus 1 dot 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 xn be a basis of V. Then we claim that so we have to find the basis of V mod U, right? So claim x1 up to xm, they are in U. So if we add x1 up to xm with U, we will get nothing new, right? So these are itself in U. So xm plus 1, so these are non-trivial element because these are not in U. Xm plus 1 up to xn plus U. So we claim that this will be the basis of V mod U. So claim this will be basis of V mod U. So for that, what we have to check that this set is linearly independent and they span V mod U. So first let's check that this is linearly independent. So I again call it suppose beta. So beta is linearly independent. So we have what is the zero element in V mod U? It's U, right? So let's take A. What is AMN? A1, let's say. A1 x m1 m plus 1 plus U plus dot 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 an minus n minus m, right? xn plus U equals to the zero element of U, not zero element of V mod U is U, right? So that's why we have written this equals to U. So what is the meaning of this? Which means a1 xm plus 1 plus dot 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 an minus m xn, this belongs to U, right? So if this is in U, we know the basis of U. We have taken this to be x1 x2 xn. So therefore we can write it as x1 up to xm is the basis of U. So you can write this, because this is an element of U, so you can write in terms of linear combination of the basis elements, which implies a1 xm plus 1 plus dot 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 an minus m xn. You can write it as some b1 x1 plus dot 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 bm xm, where b1 up to bm, these are real numbers. Now take one side all the elements, then we will get a1 xm plus 1 plus dot dot an minus m xn minus b1 x1 minus dot dot minus bm xm equals to 0. So we get that linear combination of x1 up to xn is 0, and we have taken x1 up to xn to be a basis of B. So these are linearly independent, as x1 up to xn is the basis of B. So all the coefficients should be 0, which implies a1 dot 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 an minus m should be 0. So we have get all the coefficients are 0, which implies that this is indeed the linearly independent. xm plus 1 plus x n minus m plus u is linearly independent, right? This set is linearly independent. Sorry, this is n. Okay. Now we have to show that this is span B mod W. This is also easy, you can check also the beta spans B mod U. Means you have to take any arbitrary element and you have to write down in terms of the elements of this, right? B mod A from the set beta. So now let's take some P arbitrary element from V mod U. So P will be look like P equals to some B plus U, right? And B is where B is in capital B, and B, so from B you can expand it some how A1, let's say, because x1 up to xn is a basis for B, so you can write a1 x1 plus dot 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 am xm plus am plus 1 xm plus 1 plus dot 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 a n xn plus u, and where you know x1 up to xm is a basis of u, so means, so this will simply be a m1 m plus 1 xm plus 1 plus dot 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 a n xn plus u, because as x1 up to xn this set is belongs to u, right? So this is the simply meaning what you want, am plus 1 xm plus 1 plus u plus dot 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 an xn plus u, right? So we have written down P in terms of the elements from beta, which implies span of beta is the B mod W, right? And how many elements are in the B mod W? So what is beta? Beta is xm plus 1 plus u comma dot 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 xn plus u. So the cardinality of beta is n minus m, right? And we have shown beta is a basis of v mod w. So dimension of v mod w will be n minus m, where n is the dimension of v minus dimension of u. So you have got dimension of v mod w is dimension of v minus dimension of u. So option number 4 is again, what is option number 4? Dimension of v mod w is dimension of v minus dimension of w. So this is correct. Okay, so question number 7 is done. Move to the question number 8. A subspace U of R3 is given, x, y, z R3 such that x and y both are component 0. So basically this is a one-dimensional subspace of R3, the z axis, and you have to show the following options are correct or not. So option number 1, U is given x, y, z in R3 such that x equals to 0 and y equals to 0. So this is the basically all the 0 0 z, right? 0 0 z in R3. So that z belongs to a real number. So this is the z axis. So dimension of u, from here you can all easily see the dimension of u is 1. Now what it is saying, if v1 and v2 are linearly independent subset of R3, if and only v1 plus u, v2 plus u is linearly independent in R3 mod u. So it's saying that if you take the two elements which are linearly independent in R3, then the corresponding coset, corresponding cosets will be linearly independent in R3 mod u. So let's see that this is not true. So you can easily check that 0 0 1 is in u, not, and this is a standard in the standard basis of R3. 0 0 1 is in u. So let's this two set element 0 1 0 and 0 0 1. Set it v1 and v2. Then v1 v2, this is li in R3, and what will be the corresponding coset? v1 plus u, this is 0 1 0 plus u, so 0 1 0 is not in u, so this is this coset, and v2 plus u, this is 0 0 1 plus u. So this is basically is u, because as 0 0 1 belongs to u, right? And this is the 0 vector. So the corresponding set, this set cannot be linearly independent, right? If 0 is contained in any set, this set is not linearly independent. So v1 plus u comma v2 plus u, which is the set v1 plus u comma u, is not linearly independent, as u is the 0 element in v mod u, right? So the first option is false. Now what is the next option? It's saying that if v1 v2 v3 spans R3, then the corresponding cosets span R3 mod u. Okay, so v1 v2 v3 spans R3, v1 b1 b2 b3. This span of this, it's saying it's R3, and R3 has dimension 3, and these are 3 elements, so they all are linearly independent, which implies b1 b2 b3 all are linearly independent. And we have shown that U has dimension 1, so one element among them will be in U. So let's say B3 is in U, as U has dimension 1. Right. Then what we have to check? That the corresponding coset will span R3 mod U. Then B1 plus U, B2 plus U, B3 plus U. So B1 plus U will not be so B3 plus U is, this will be again U, because this is the B3 is in U. So this will span the R3 mod U, right? We have seen that if B1 B2 is in outside the U, and they are linearly independent, means they are the, because these are, this forms the as B3 is basis of U, and you can view as this set as extension of the basis of B3 to the whole B, and B1 B2 B3 is basis of B, right, or R3, B equals to here R3. So by the by the question number 7 you can see that. So therefore by exercise 7, last option, B1 plus U and B2 plus U will be basis, right? Will be basis of R3 mod U. So which means this set B1 plus U, comma B2 plus U, comma B3 plus U spans R3 mod U. So option number 2 is correct. If this B1, B2, B3 spans R3, then the corresponding cosets span R3 mod U. Now what is the next option? If B1, B2, B3 forms a basis of R3, then corresponding cosets form a basis of R3 mod U. You can see from this example itself that this is not true, right? So option number 3 from 2 we have seen, we got B1, B2, B3 basis of R3, and we have taken B3 to be U, is in U, right? So B1 plus U, B2 plus U and B3 plus U, this set will be, so B1 plus U, B2 plus U, and this is the U, 0 vector. So 0 vector is in this set, so this set cannot be linearly independent, as the 0 vector, this set will be spans R3 mod U, but this set is not linearly independent, as 0 vector U of R3 mod U is, let's say this set to be beta, is in beta, therefore beta is not linearly independent. So therefore this will not form a basis. v1 plus u, v2 plus u and v3 plus u will not form a basis for R3 module. So the option number 3 is wrong. Now let's check the option number 4. If v1 plus u and v2 plus u is linearly independent subset of R3 module, then v1 v2 is linearly independent. Okay, so let's check this. Option number 4. So given v1 plus u and v2 plus u is linearly independent in R3 module, what you have to show v1 comma v2 is linearly independent in R3. So let's take the linear combination. C1 v1 plus C2 v2 is 0. So we have to show C1 C2 is 0. So then what happened? C1 v1 plus C2 v2 plus, if we add u, so it will be u, means if you add some element of u, it will look like this. So from there you can write C1 v1 plus u plus C2 v2 plus u is u, and u is the zero element of R3 module, and as this v1 plus u at this set is linearly independent, as v1 plus u comma v2 plus u is linearly independent, so which implies C1 C2 is 0, right? So which says that v1 v2 is linearly independent. v1 comma v2 is linearly independent. Linearly independent in R3. So the option number 4 is also correct. Okay, now let's check the option number 5. If v1 v2 be vectors in R3 such that v1 plus u and v2 plus u spans R3 module, then v1 v2 v3 does not spans R3 or any v3, right? So it's saying that if v1 and v2 be the vectors such that v1 plus u and v2 plus u is span R3 module, then it's saying that then the v1 plus v2 v3 does not span R3 for any v3. So we will give a counter example. So let's do it. So this is option number 5. So let's do vector. Take v1 to be 1 0 0 and v2 to be 0 1 0 and v3 take 0 0 1. Then we have already seen that v1 v2 does not belongs to v3, right? Then v1 v2 does not belongs to u and v3 belongs to u, right? So therefore v1 plus u and v2 plus u spans R3 module. and this is and v1 v2 v3, this also spans R3. So we have get a example where v1 plus u and v2 plus u spans R3 module, and also the course v1 v2 v3, this is v3, spans R3. So therefore the option number 5 is incorrect. Okay, so question number 8 is done. Okay, so question number 7 is done. 8 is done. Let's move to the question number 9. What it is saying, P3R means this is a set of all polynomials of degree less than equals to 3 with real coefficient, and W and W naught, two subspaces are given. You have to find the V mod W. Question number. So V is P3R, and we all know the dimension of P3R. What is the dimension of P3R? So this is 4, right? Because 1x, x square and x cube is a basis of P3R. So let's find the dimension of W. So what it is in W? W is P belongs to V such that P dash 0 equals to P of 1, right? So let's take any polynomial in P3R. So it will look like P of x will be a0 plus a1x plus a2x square plus a3x cube. So then what will be P dash 0 equals to P of 1? Then P dash 0 and P of 1, which imply a1. What if you differentiate? So a0 will be 0, a1. So P dash 0 will be a1 will be only there. a1 equals to P of 1. So simply put P of 1, P dash 0 so this is 0, a1. So note that this will be a1 dot 0 plus 2 a2 dot 0, sorry, a1 nothing will be there, plus 3a3 dot 0 means a1. And what is P of 1? P of 1 is a0 plus a1 plus a2 plus a3. So you will get a0 plus a1 plus a2 plus a3, so which implies a0 plus a2 plus a3 is 0, right? Means you can write a0 as minus a2 minus a3. So let's put it in general polynomial. So the polynomial, therefore P of x will be a0 plus a1x plus a2x square plus a3x cube. So a0 is minus a2 minus a3 plus a1 can be arbitrary and polynomial. a1x plus a2x squared plus a3x cube. So therefore this you can write a1x plus a2, you can take common out, minus 1 plus x square plus a3 minus 1 plus x cube. And you can check this is a linearly independent set. X minus 1 plus x square, and this will be minus minus 1 plus x cube is linearly independent in P3R, right? So and spans of, so therefore W will be span of x minus 1 plus x squared minus 1 plus x cube, right? So dimension of W is 3, and we have dimension of V, which is P3R, is 4. So dimension of V mod W, what will be dimension of V mod W? Dimension of V mod W, so this is dimension of V minus dimension of W. This is 4 minus 3 will be 1. So dimension of V mod W is 1. Okay, question number 9 is done. Let's move to the last question, question number 10. Here you have to find the dimension of V mod W naught. So first you have to find the basis of W naught. What is W naught? W naught is all such P is in P3R such that P dash 0 equals to P of 1 equals to 0, right? And we have taken P, take arbitrary polynomial a0 plus a1x plus a2x squared plus a3x cube. So then what will be P dash 0? P dash 0 will be a1, and P of 1 will be a0 plus a1 plus a2 plus a3. So these two equate this to 0, which implies P dash 0 is 0, imply a1 equals to 0, and P1 equals to 0 imply a0 plus a1 plus a2 plus a3 equals to 0, and we already get a1 equals to 0, which implies a0 plus a2 plus a3 is 0. So just write a0 equals to minus a2 minus a3. So therefore general polynomial will look like ex a0 plus a1x plus a2x squared plus a3x cube. A0, put it a2 minus a3, a1 is 0, so this is a2x squared plus a3x cube. So then take a2 common out in minus 1 plus x squared, plus take a3 common out minus 1 plus x cube, and now you check that these two is, so W naught, okay, and check that this set minus 1, minus 1 plus x squared and minus 1 plus x cube is linearly independent, this set in P3R. Right. So then we will get W naught will be span of minus 1 plus x squared, comma minus 1 plus x cube. So therefore dimension of W naught will be 2. Then what will be dimension of V mod W naught? It will be dimension of V minus dimension of W naught, means dimension of V, which is P3R, which you know it's 4, and this is 2, means dimension of V mod W it's 2. So the answer is 2. Right. So question number 10 is done, and this finishes the assignment 5. Okay, any question? Yeah, if there is no question, then let's end it for today. Okay, bye.
Thank you, sir.
Bye.